Hey Team Bio, so at this point in time, we have discussed the light-dependent reactions, as well as the overall goal of photosynthesis. And while it still might be a little bit confusing to you, hopefully you're getting acquainted with these reactions. They're very complicated, so this is going to take a little while. But hopefully the puzzle is helping, or maybe it's making it worse, who knows. But tonight's screencast is on the light-independent reaction. So before we dive into the light independence, just a quick review of the overall equation for photosynthesis. Okay, so we know that the inputs for photosynthesis are CO2 and H2O, and then the outputs, and then also light, are all the reactants and necessary ingredients in order to have the reaction happen. And then the outputs are glucose and oxygen. Well, looking at the equation, you can see that we've already seen some of these things come into play. We know that light was necessary in order to run the light-dependent reactions. It is collected by the photosystems, and we actually have seen already the utilization of oxygen the utilization of water and the production of oxygen also in the light-dependent reactions. So let's write down here. I guess I'll do this in yellow. Water is consumed in the light-dependent reactions, and oxygen is produced. And this both happens in, I'll remind you, the stage of photosynthesis, actually at the very beginning, called the photolysis of water. Where water is split into its component parts, so hydrogen ions, H+, electrons, and oxygen. The oxygen is a waste product. The hydrogen ions become part of the concentration gradient that exists between the stroma, I messed it up, bad student, the stroma and the lumen of the thylakoid membrane system. And the electrons are passed down the electron transport chain. They are the low energy electrons that become high energy electrons, or the He. And then also produced in the light dependent reactions, ultimately we get NADPH and ATP. Okay, so what's left? Well, we need to somehow consume CO2 and make glucose. And so guess what? That's going to happen in the light-independent reactions. So as I said before in our last screencast, ATP and NADPH are the molecules that are produced in the light-dependent reactions that are going to power the light-independent reactions. So with CO2, a little bit of water, we are going to make a few things. Well, first, we're going to split ATP to ATP and free phosphate. And we're going to send these things back to the light-dependent reactions. We're also going to use up our NADPH, and we're going to turn it back to NAD+. And all of these things, all of these components are going to go back to the light-dependent reactions to get recharged back up. But the thing we're going to make in the light-independent reactions that's so important is this molecule called pGal. which is a 3-carbon compound, and it's a precursor to glucose. And this is the ticket. This is what this whole crazy scheme is for, is to make this pGal molecule so we can make glucose. But just once again, quickly, connecting these two reactions together. Here's our overall reaction. We saw these two things consumed and produced in the light-dependent reactions. So this leaves carbon dioxide and glucose to produce and consume. We also know that NADPH and ATPH were made in the light-dependent reactions. So if we look at our chemical equation for the light-dependent reactions, we see it's powered by these two molecules. We're going to consume CO2, a little more H2O actually, and we're going to make pGal. And we're going to return these broken down components. Their energy has been released now. We're going to turn them to the light-dependent reactions where they can get charged back up again. Okay, so this is going to be a long screencast. I apologize. The light-dependent reactions. We know that they're called many different things. In our class, we're calling them the light-dependent reactions, but you also see them called the Calvin cycle or LE. So that's how you spell cycle. You'll see them called the Calvin cycle or the dark reactions or the Calvin Benson-Basham cycle or the reductive pentose phosphate cycle or the C3 cycle. And they all mean the same thing. Okay, but they both happen, or it's all the same thing. It happens in the stroma. So that jelly-like space that's in between the inner membrane of the chloroplast and the thylakoid membrane system, this is where the reactions are taking place, in the stroma. Okay, it's a cycle, so we could start anywhere, but we're going to start in this upper left-hand corner with a very special molecule, CO2. You should write to the side because there's going to be something that goes in the space here, but I'm not going to write it in until later, so leave a little space off to the side. So although this looks complicated and like we're doing a lot here, we're actually not talking about a lot of the enzymes or different intermediates, what they're called in this set of reactions. But we are going to keep track of carbons. So another name for this activity could be always count your carbons. And we're going to track where carbon goes around the cycle. Each of these black little C's represents one atom of carbon. So you'll see here, we start with CO2. CO2, as you know, comes into the plant through the base, a structure at the base of the leaf called the stomata, or the stoma, singular, and the source is the air. CO2 is smashed together with a 5-carbon compound called RUBP. And so if we count up our carbons, we see there's 1 here, 1, 2, 3, 4, 5. If we smash 1 CO2 with a 5-carbon compound in this crazy enzyme, which is actually the most abundant enzyme on Earth, called Rubisco. So Rubisco binds this RUBP and binds the CO2, and it smashes them together into a 6-carbon compound. And this, so we had 5 carbons, we added 1, we got a 6-carbon compound here. Rubisco catalyzes this reaction, and this 6-carbon compound is actually really unstable. So it spontaneously breaks in half. Now we are left with 3-carbon compound, or 2 3-carbon compounds. Well, we'll get into the numbers later. Just think of it as one. It's a 3-carbon compound called PGA. This, so 1, 2, 3. This 3-carbon compound is not very high energy. And so in order to charge it up, there are a few things that have to happen. We've got to donate some ATP to it, and we've got to donate some NADPH to it. And remember, both of these components are being supplied to the reaction from the light-dependent reactions. So ATP comes in and drops off some energy. Whoops. Undo that. And NADPH, also coming from the light-dependent reactions, comes in and drops off some hydrogen ions and some high-energy electrons. And then NADP plus comes out of this and returns to the light-dependent reactions to be made into NADPH again. And ATP is broken down into ADP and phosphate, and is also sent back to the light-dependent reactions to be charged up again. And so these little 2 starbursts represent a series of chemical reactions. But the end result of the energy from ATP and the high energy electrons from NADPH is a very high energy molecule that we call pGal. Which is a 3-carbon compound. 1, 2, 3. Okay. So pGal can be used to make glucose. And hold off a sec on judging these. Okay, bear with me. We're going to get there. Okay, so in order for this cycle to be complete, we've got to return pGal back to RUBP. And the way that's accomplished is if you take pGal and, which is again a 3-carbon compound, and you add a little water that comes via the xylem, and the source is the soil. And a whole bunch of reconfiguration reactions take place, supplied with a little bit of ATP from the light-dependent reactions. And again, we get back out some ADP and phosphate, which is going to, again, be sent back to the light-dependent reactions to be charged back up into ATP again. Oops. We can reconfigure this pGal into RUBP. Oh, I don't know when my purple color changed. Okay, but if you're looking at this image, you'll probably notice that, well, I've left an area blank here. And this is for a reason, because we're going to count up all the carbons now. So we'll start with glucose. Glucose has 6 carbons. It is a 6-carbon compound. In order to make 1 glucose, which I forgot to do this, glucose is a high energy molecule, so I'm going to style it in pink here. In order to make 1 glucose, we need to use 2 p-gals. P-gal is also a high energy molecule, so it gets colored in pink. So our goal is to figure out how many times does this cycle need to run such that it can keep running and we can make glucose. So bear with me, back up here. Imagine we start out with 6 CO2 and we combine 6 CO2 with 6 RUBP. We're going to get 6 of this 6-carbon compound that's highly unstable, which spontaneously breaks in half, and we're left with 12 PGA, right? If you take 6 carbon compounds and you slice it in half, then you are left with 12 3-carbon compounds. These 3-carbon compounds are charged up with energy, but it doesn't change the amount of carbons in them. So out of this series of chemical reactions, we get 12 p-gal. Of these 12 p-gal, we are going to take out 2 in order to make 1 molecule of glucose. And then we're left on this side with 10. 10 3-carbon compounds is equal to 30 carbons total. If we take these 30 carbons, these 10 3-carbon compounds, and we rearrange them in a whole bunch of reactions powered by a little bit of ATP, we get 6 5-carbon compounds. 6 5-carbon compounds is equal to 30 carbons total. So we haven't gained or lost any carbons running around from p-gal to RUBP. So essentially, what this is telling you, all these numbers here, is that this cycle has to spin 6 times in order to make 1 molecule of glucose and have enough carbon left over to continue the cycle going again. So the Calvin cycle spins 6 times in order to make 1 molecule of glucose. Okay, and that's it. Easy peasy, lemon squeezy screencast. Sorry about the length. See you all in class on Thursday or Friday.